So, welcome everybody. It's a great pleasure to introduce our friend and colleague, Prahladh Harsha. Prahladh got his BTech in computer science from IIT Madras, then a PhD from MIT. He was a postdoctoral researcher at the Toyota Technological Institute in Chicago, then at Microsoft Research in Silicon Valley. Before joining the School of Technology and Computer Science at TIFR Mumbai, where he's currently a professor. Today, as his t-shirt suggests, he will be speaking on high-dimensional expanders. Welcome.
Thanks, Jaykumar. Yeah, so like Jaykumar introduced me. I knew of Jaykumar. I met Jaykumar at my postdoc place, Toyota Technological Institute, where he sort of convinced me to, sort of coaxed me into joining TIFR, or rather induced me, and I've been there since. It's been a great 12 years. So the topic I'll be talking about today is high-dimensional expanders. This is sort of a recent burgeoning topic in theoretical computer science and in the general scientific community itself. Mathematicians have been working on this topic for about a little more than a decade, and theoretical computer science for about 5 years or so. I have been actively involved in this, not in the last year or so, but prior to this, I've been very actively involved in this area. But I thought this is a very fertile ground for people from different backgrounds, math, physics, computer science, to come and have a look. That's why I'm sort of giving, what I will do is I'll hardly spend time on work which I have done, but give a sort of survey-ish talk on what's happening in this one, giving sort of intuition for what high-dimensional expanders mean and stuff. I don't have a full-fledged, I have a plan to give the talk, but I don't have to cover all slides, so feel free to stop, interrupt me as much as possible. We can stop at any point of time. It will be good enough. So this is meant to be a sort of a survey-ish area, sort of trying to tell others about the magic that's been happening in the world of high-dimensional expanders, which has been a very active interest in mathematics and computer science. So let's get started. So before we go, so what are high-dimensional expanders? So first, let's start with what are expander graphs. So let's start with this more basic object of expander graphs. So what is an expander graph? An expander graph, so what's a graph firstly? A graph is just for us a set of vertices and some interconnections between them. That's all a graph means. It's a bunch of nodes and connections between the nodes. Such as this one, the road network, it's an internet network. Any one of these is a graph network. And what are expander graphs among them? Expander graphs are those graphs among these which are extremely well connected. That is, every node is sort of very well connected to there's a very short path or something. You can go from one node to another node very fast. Of course, the best sort of expander will be the complete graph in which every pair of nodes is connected. In the next few slides, we'll try to see an attempt to define what this notion, very informal definition of what very well connected means. So, and this is a notion that has appeared in different scientific disciplines, this notion of expansion, and they have actually come up with different definition notions of way of formalizing this notion of well-connectedness. And we'll see a few of these examples. The nice thing about it is, even though different groups came up with this and came up with different definitions, these definitions happen to actually morally equivalent definitions, this notion of expansion. So I'll start off, being a computer scientist, I'll start off with the sort of the computer scientist notion of an expansion. So what's the expansion over here? Expansion, so once again, a graph is just a set of vertices and interconnections between them. Expansion for me here is for any subset of vertices, for any subset S of vertices, say this is a subset. As long as the subset is not larger than half the number of vertices, then the neighborhood of the vertices, that is all those vertices that are connected by just one edge from this vertex, is at least some fixed constant times the size of the set. That is, each time you take one step from a set, you actually see a large number of neighbors. It can't be that all of its neighbors is just one vertex. There's just one outside vertex. So each time, if you are in a small set of vertices, a small is not larger than half the vertices. When you take a step out, you see you grow by a factor of at least a. You think of a as a fixed constant. 0.8, 1.2, 1.3 is a fixed constant. So in some sense, as long as you're not reached more than half the set of vertices, each time you take a step, you keep growing. Think of a actually as a number larger than 1. So you keep growing each time, and eventually you will hit half. So that's the notion of expansion. It's a combinatorial notion of expansion. N of x is just the neighborhood.
But for each, neighborhood for each element of the set, or
it's just the N of s is just the set of vertices which are connected by one edge to the set S. So for instance, there could be two different, for example, for this, it will be these three vertices. It's the boundary of the set. Huh? The one-step boundary of here.
Union of all the nearest neighbors of everything that's inside S.
Yes, yeah. Yeah.
In a case where everything is connected to everything else.
Yeah.
You don't grow at all.
No, you will grow. The moment you take a step, you grow to everything.
That's what we do. But let's say I already have 3, then everything is already connected by distance of 1. If I take a step, then.
But there, no. What do you mean? So if it's a complete graph and you pick a set of size 3, the moment you take a step, one step, you hit the whole thing.
Oh, I see. That's what growth means.
How many new guys you keep seeing this? You think of this, okay, from a computer science point of view, you're a packet on the internet network. How fast you have to move to before you see the interest. So this is very common in social media or gossip networks. How fast does the gossip have to reach the entire community? And that's what I'm talking about over here. We won't go into this definition. We'll go to other definitions which will be more interesting. But this is sort of the computer science-ish definition. There's a more spectral definition which the mathematicians are more used to. It's just look at the adjacency matrix of this graph. That is, draw the matrix, the n by n matrix. N is the number of vertices, in which you put a 1 if the vertex ij are connected and 0 otherwise. And so let's sort of normalize the adjacency matrix. Let's divide each entry by the degree. These are undirected graphs, by the way. You divide it by the degree, and let's look at the eigen spectrum of this particular graph. And it's not hard to see that the largest eigenvalue will be of eigenvalue 1. And I'm going to look at what's the next largest eigenvalue. Either it's lambda 2 or the absolute value of the smallest. This should be bounded away from 1. It should not be 1. The largest is 1. It must have a constant gap. That is, it will be certainly less than or equal to 1, but I want to say it's not less than or equal to 1. It's actually, say, 0.99 or something. This is a definition of expansion. This is what's usually called spectral expansion for a graph. And another definition is a random walk. That is, you start with some unknown distribution, some distribution on the set of vertices. This could be the delta distribution also. So it is a distribution which is concentrated just on one vertex. And then you sort of begin doing a random walk. At each step, move to a random neighbor and ask how well does this eventually go to the stationary distribution, which is the uniform distribution on the graph. You could ask how fast is the convergence times, and that will be a notion of if it mixes very well, then you call it an expander. And this is formally said as, if you look at A, which is the adjacency matrix, that sort of represents the transition. The normalized adjacency matrix will exactly represent the matrix of transition probabilities. That divided by the thing that mixes perfectly, that is J by N. J is the set of all ones matrix, that is, it goes to a random, ignores the edge structure of the graph and just goes to a random vertex. The difference between those two in the spectral norm should be lambda. That is, these two spectrally should be very close to each other. That's one way of formalizing the random walk definition. And in fact, if a little familiar, this is in fact, though I stated it in a different way, this definition and the previous definition which I put are exactly, it's not just the morally equivalent, they are verbatim the same definition. So this is the random walk definition of expanders. The nice thing about expanders is, so people looked at it from various points of view, they have different definitions, and strange thing is the very first definition which I gave is also equivalent to this definition. There's a loss of parameters, but anything that's a combinatorial expander is necessarily a spectral expander, and a spectral expander is a combinatorial expander. So you, for example, if there's a which is larger than 1 here, that will mean there's a mu which is greater than 0 here. And if there's a mu which is greater than 0 here, it will mean there's an A which is larger than 1 in the previous slide. A is usually larger than 1. So you expand, you actually expand. Okay. And these appear in a lot of contexts. Yeah, so that's this one. Of course, in all of these contexts, if you look at it, what are we comparing ourselves? You say the gold standard of connectivity is the complete graph. The graph which is completely well connected is completely connected. Every pair of vertices has a node. This certainly mixes extremely well. Its combinatorial expansion is as good as it gets. It's the large best you can hope for. Spectral expansion, mu is 0. Mu is 1. It's all the way. The second eigenvalue is 1. So this is extremely good one. And whenever we define a notion of expansion, there will be sort of a gold standard of connectivity, which will, in this case, it's the complete graph, and we want to mimic it in several ways. And in fact, if you look at the random walk definition, it is exactly mimicking it. This is sort of the complete graph, and you're saying that this graph is as close to it in the spectral sense. Sure.
This first definition you gave, the combinatorial expansion.
Yes.
Does that have to be true for all subsets?
Yes, all subsets, yes, which are smaller than half the size. Because after half, you can't, any sets smaller than half, this should be true. Okay. And so, if the complete graph is the gold standard of connectivity, one would think that such a graph, a complete graph, how many edges does it have? An n vertex complete graph, it has quadratically many edges. You can ask, which are graphs which have such well connectivity? The complete graph has it. Are there even sparser graphs, sparser networks which have such good connectivity? An amazing thing about expanders is there actually exists graphs which have constant degree. Every node is constant. The constant can be really small. It can be as small as 3. You can't have 2. 2 will be just union of cycles. You go just to the next step, 3. There exists degree 3 graphs which are expanders in all the definitions I meant. And how do you find such an expander? Actually pick a random 3 regular graph. It will be an expander. Just a random 3 regular graph. Define a notion of random distribution. Just pick one. It's going to be an expander with very high probability. But here, this dev class have the extra word here, explicit. I want to say that it's not just a random one. You can actually explicitly construct such. I can give you a procedure that will construct such an expander. There exists this one, and this is a very, very useful fact, at least in theoretical computer science. This fact has been led to several applications in computer science. So they exist. Expander graphs are abundant. A random graph, a random constant degree graph is in fact an expander. And furthermore, we can construct these constant degree graphs extremely efficiently. They are very good algorithms to construct these.
Random walk on some input always like it's connected to always spread.
Yes.
And sometimes
yes.
Will be called an expander graph. Like this will be sometimes.
So time scale, so you would require so typically the complete graph, of course, the time scale is 1. So typically these will be log n, log the number of vertices. By that time, you will typically reach the uniform distribution. You will converge to the uniform distribution within time log. No, not finite time. The time should be logarithmic in the size of the vertices. So when I mean expander graph, so okay, there's one thing which I always do. So we don't build just one particular expander graph of a particular size, like not 1,000 vertices. I'm interested in a family of expander graphs. I want expander graphs of 1,000, 1,001, 1,002, and this growing family of graphs. For every n that you specify, I want an expander graph on n vertices. But the degree is constant. Say all of them are 3 regular graphs, and all of them I want their spectral gap to have the same constant A or the same constant mu. So each of these, once you have that, the mixing time of these graphs will be logarithmic in n. So even though the graphs is growing, it's n, the mixing time will be just a small, very small function of n. It's not going to take. Yeah. So yeah. Yeah. Yes. That's the intuition. In fact, that will be the proof. Formalize that. If you drop the word explicit, that's the proof of that fact.
But now, let's say I go beyond what I'm trying to understand. Let's say I go beyond n by 2, so I have now more than half or 99% of these things.
Yeah.
Then there's a 99% probability I'll pick something in that set.
Yeah. So if you refine my, yeah, it goes down, but there actually my definition of combinatorial expansion, I was very careful to say I will expand only for sets of vertices, not larger than that, because at that point I can't expect expansion. It's going to begin. So you already hit half, but you're expecting. If you're thinking of this as a gossip network, there's somebody wanting to spreading the gossip. There's wanting to hear the gossip, and those two sort of graphs meet at this point. Yeah. So that half is what we'll take care of.
So if you have just a tree which is bivalent tree,
yeah,
that's not
an expansion.
So that's even though it's not a random.
It's not a random. So a random graph will not in fact have be a tree-like thing. Yeah.
So okay. So you need cycles. Is that what
you will certainly have cycles? You will certainly have cycles, but you can show. You can actually expanders might. If you build it randomly, they might have small cycles, but you can also show that you can construct these graphs. This one, explicit construction. We know of constructions which locally don't have any cycles. Locally, if you walk for logarithmically many steps, you will encounter only a tree-like structure. The expansion is coming in a much further structure. That is, the global structure is expanding. Locally, when you look at the piece, you cannot distinguish from a tree. And they do exist, such constructions, not the random constructions, but the explicit constructions do have these properties.
And when you said in your definition that for all subsets S,
yeah,
that all is very crucial.
That all is important. So in
even fact, if you allow almost all.
So once you give me this one, I can show. These two things, the two different definitions, the combinatorial and the spectral. If you give me a counterexample, using that I can give you a counterexample the other direction. I can go back and forth this way. Yeah, so all is important over there. Questions? Yeah.
So if I consider the ensemble of random regular graphs,
yeah,
where the degree grows in some way with the size of the graph,
yeah,
however slowly it may be, take log. Can I say that with probability 1, I'll have an expanded graph?
Probably almost surely you'll have. In fact, I'm saying you don't even have to have the degree going. The degree could be 3.
No, but I want probability 1, that every member of that ensemble should be an expander.
No, that I don't think I will be able. I'll get almost surely. I'll get 1 minus little o 1.
Even if the connective degree grows.
I think you can construct graphs with very large degree, which are not expanders. Okay. You can certainly construct large degrees. So, yeah.
So you're saying if I had a tree with any number of that would not be an expander?
Tree is not expand. Trees are not. Any number.
So that would be, I guess, something where you have.
Yes, because that's definitely one example of. Yes.
Arbitrarily many
examples.
One minus 1 by n, you're counting as 1. You want 1 in the limit n goes to infinity.
No, I want. No, I really want finite.
Yeah. So you have to define the distribution on graphs properly, and I don't see any natural way in which you can escape. You can get perfectly 1. I don't see it. There might be definition, but I don't see it. Yeah. Huh. And so that's this is an amazing. This was sort of. By the way, I should have mentioned this was. I had given a shorter version of this talk in the Kolmogorov day. And the notion of expansion, at least in the computer science literature, started from the study of telephone networks and this one, Pinsker. But then later on, we now know that actually this was one of Kolmogorov's works. He actually studied it when trying to understand how the brain works, the neural networks. He modeled it as an expander graph, that is, how the neurons connect to each other. And this is work of Kolmogorov and Basdin. So to our knowledge, that's the first work that talks about expansion in graphs. That was for, he modeled it basically on a random graph, and Kolmogorov and Basdin modeled it on random graphs. But these graphs, this fact that they exist explicit graphs, which have even constant degree graph is expander, has had innumerable applications in theoretical computer science. In fact, metric embeddings, telephone networking, random walks and mixing times to understand certain random walks. So there have been time-space trade-offs, Byzantine agreement, error correcting codes, de-randomization. I'm just going to a laundry list of applications. It's not just being used as tools for certain things, it's also being used as sort of so certain very important theorems in theoretical computer science have had simpler proofs because we have the construction of expander graphs. They've been used as more an analytical tool, not just for computer science applications, or sort of this is a computer science application, but it's more goes into the proof of a theorem, the fact that such expanders exist. There have also been several coding theory applications. Let's not go into this. What I want to actually go now into this talk is, this talk was not about expanders, it was about this topic called high dimensional expanders. So we're going to move from expander to what's a high dimensional object of it. So what do I mean high dimension and stuff? Firstly, what I mean high dimension is, now I want to move from graphs. What are graphs? Graphs are vertices in which you have a node, you have links between pairs of nodes. So suppose now you move to graphs, to hypergraphs, in which the link is not between a pair of nodes, but a set of nodes. Like 3 nodes you have hyper edges rather than edges. So the edge now no longer is just 2 vertices, it contains more than 2 vertices. For example, an object like this. So this has 7 vertices. This is an edge which just contains 1 vertex. The yellow is an edge which contains V1, V2, V3. The green is an edge which contains V5, V6, V3, and so on. The edge structure could be this, and I would like to define a notion of expansion for this object. That's where the high dimension is going. High dimension is the dimension which you're going to increase is the number of vertices per edge. I want to increase and define a notion of expansion and ask how useful this notion is going to be. Okay? And especially given how useful notion of expansion has been in math and theoretical computer science, I'd like to know, are there nice definitions which have the same universal feature in this one? So there have been several candidate definitions. We have taken each of these definitions that I've seen, the spectral definition, the random walk definition, the combinatorial definition, and extended them in a particular way to the high dimensional scenario. There have been several such things. For example, in the computer science world, Louis Yoshida and Soma Yoshida had extended the spectral viewpoint or the Laplacian viewpoint to this one. So one nice thing about the spectral viewpoint in graphs, it has a very linear algebraic flavor. This will lose the linear algebraic flavor when you go to hypergraphs. Then in the math community, Lineal and Meshulam and Gromo had suggested notions of expansion. They were looking at it more from the topological point of view, or cohomological expanders, co-boundary expanders. I'm not going to go into these. There have been such definitions. Out there was one such definition which is called link expanders. And this is sort of the definition which I'm going, link expanders, and then a definition which extends the random walk notion of this one. That's going to be, in fact, most of my talk, all my talk, I'm going to focus on these 2 definitions. And this is a very recent area. So unlike expansion, in which all the different definitions are all morally equivalent, these definitions are actually not equivalent. You can show that there are graphs which will be an expander in one way, in one viewpoint, but not an expander in the other viewpoint. But what I want to, what now we actually call high dimensional expanders is expanders along these 2. So what I want to impress on you in the next 20 minutes or so is I'll try to give a natural definition using the random walk, this one for higher dimensional objects, and then hopefully it will be a pretty definition once I give it. Then we'll ask, is the definition useful? If it's a nice definition, is there any use? And we'll try to see an application of the definition by the end of the talk. So the goal is this. We want to extend this notion of expansion definition to higher dimensional objects. Yeah.
When you say H4 has just 1 vertex.
Yeah.
Like typically H has 2 vertices.
Yeah. So hypergraph, I'm allowing these things very soon. So just see 1 second what I'm going to do. So we will, so I will not go to this general definition. We will work with, say, K uniform hypergraphs. That is, every edge will fix a K. The usual notion of graph K is 2. We'll fix K to be 3, 4, 5, one of these, and talk about K uniform hypergraphs. That's our definitions eventually will go to that. This was just for this is just a cartoon along the way. And once again, whenever all these definitions are motivated by the fact that how did we define expansion in the 2-dimensional world? In this one, the complete graph was our gold standard of expansion, and these definitions were such that expander was defined so that the complete graph was a good expander, and you were trying how well the other graph mimics the complete graph in some quantitative sense. That was the way we defined expansion. And we try to take the same approach here. We will define some feature of expansion, which the complete graph perfectly satisfies. And we'll try to say, we'll come up with a quantitative notion for this and say, and the graph is supposed to be a high dimensional expander if it has this feature. That's going to be the way we do it. So what's the complete, if you're working with hyperedges which have k vertices, what's the complete graph here? It's the k uniform complete graph. So in particular, this thing has 1, 2, 3, 4, 5, 6, 7 vertices, and the edges are basically of hyperedges of size 3. This is a complete K3 uniform complete hypergraph on the set of 7 vertices. Whatever notion of expansion we define, this should perfectly satisfy it, and we'll come up with a definition that even sparser versions of these graphs satisfy expansion. That is, just like in case for the graph case, you know, the complete graph which has n square vertices. This is not complete. Okay. Okay, this was supposed to have come on one, not at the time of K uniform complete graph, but I'm just going to work with K uniform complete graphs, not in which hyperedges have different number of vertices. Okay, so I want to now define a notion of expansion for these. So think of K as, I think there are 3 vertices which are not connected. For example, this, and this. Yeah. No. So I would need another circle for that. If I had put the other circle, possibly it would be. Actually, I don't know. I've taken this graph somewhere and I have no clue about it. This is just an example of a 3 uniform hypergraph.
This has the property that every 2 vertices have a unique edge.
Every
since is only 7 choose 2.
Okay.
Not 7 choose
3. Okay. So, and to define this, so okay, the next few slides are going to be this. I'm going to define the. Go ahead. Yeah.
Question for K greater than 2.
Yeah.
You not just replace every hyperedge with a well-connected subgraph.
So you could do that. You could just define. You could just look at what this is. What we'll call. You given a hypergraph. You just look at the link, the one skeleton of the hypergraph, which is just if 2 vertices together participate in a hyperedge, put a link between them and say that this one, and ask that this structure should be a good expander. That is a definition, but it loses completely the hypergraph structure. It ignores the hypergraph structure of it. I want to somehow, so that firstly, all our definition of expansion, the skeleton will also be an expander, but we'll demand more from it than just asking that the skeleton be. This is what I'll call as a one skeleton of a hypergraph. A one skeleton of a graph is just the graph itself. When you go to hypergraph, this will be the what we call the skeleton of a graph. We would want that to be an expander, but I will want to even more, because I want somehow, because that ignores the hypergraph structure completely. So the definition will be more complicated than the previous definitions. So we'll firstly adopt a simplicial complex viewpoint. What do I mean by that? So what I mean, math, combinatorics wise, what I mean is just downclose the set. So in other words, suppose this was your hypergraph. These are all the hyperedges. These are hyperedges of size 3. I just put the hyperedges of size. Yeah. Okay. Huh? Think of K even as 3 now, groups of 3 people.
Each of them are surrounded by what I call an edge.
No. So vertices are still single nodes. Those are the people, and then the edges are just collections of 3. That's it.
There are many groups of 3 people, and every circle I draw around and I call it.
That you call an edge. Yeah.
You want to ask now how fast the message
We're going to ask some notion of expansion. If it was just a skeleton, if you're just going to send it to some person in your group, then you're just looking at the skeleton structure of the expander. It really doesn't matter that they participated in a group of size 3. As long as these 2 were in a friends, that's all matters. So we're going to have a more richer definition of expansion. So right now, the way I'm going to do it is I want to give a definition that respects the high dimensional viewpoint. It will be only for the first next 10-15 minutes, it will just be a pretty definition. And then I will later on show an application where actually this definition, it's not just a pretty definition, it has a non-trivial application. So the way I'm motivating the definition, So this definition came from different communities. The math community here, this is more a CS definition, but to motivate it from the application will take me way too much time. So let me actually plunge into the definition. I'll take some time and then we'll see the application. Okay. So what I'm drawn here is just the hyperedges. By the way I've drawn it here is as if all the three groups of three people are disjoint. This is not necessarily the case. The groups of three people could have overlaps and stuff. For example, it could be you have all the n-choose 3 triangles over here. This is just a cartoon for this one. So let's take that and let's sort of downclose it. What do I mean by that? So I will add to it. So this is groups of size 3. I'll add groups of size 2, groups of size 1, and the empty set. That is, take any subset of the original hyperedge and call them also as hyperedges. So you're going to look at this layer. So once you give me a K uniform hypergraph, in this case it's a 3 uniform hypergraph, we will look at this layered structure in which this is 2 vertices are connected by an edge here if those 2 vertices were in a group in the previous layer. Here you have just the vertices. So notice that this will just be the set of vertices. This layer will just be the set of vertices, and this, because I'm just downclosing it. Downclosing is basically I'm viewing them as subsets of the original space, and these are all, I'm taking every subset and adding all possible subsets of this one. This is just a family of subsets. You'll have this final set is the empty subset. So given a K uniform hypergraph, we'll immediately mentally think of this picture. We'll look at this layered picture. So if it was a graph, it has only these 3 layers. Now once you go to K greater than equal to 2, K greater than 2, you have this layer also. And just talking about expansion, if you look at the skeleton, you're only looking at these 3 layers and the expansion is talking about here. I want to define an expansion which somehow uses the top layer also. Uses the structure of the top layer. That's going to be question so far. So
it is like what I guess you're going to say. It's like a high dimensional simplex.
Yeah, this is a high dimension. This is a simplicial viewpoint, viewpoint of the structure.
You should do then the 3 uniform things as the set of faces of some.
Yes.
Simplex.
Yeah, exactly. Okay. And I want to define a notion of expansion over here. So and for natural reasons, this one I'm going to call, remember this is the set of, if you had worked with a graph, you have only x0, x1 and x2. x1 is called the set of vertices and x2 is the set of edges. Here naturally I'll call these triangles and so on. I'm going to call them as quadrilaterals, and those will be the various size of edges. This one. So what we're going to do in the next few slides is try to extend this random walk definition that we had for graphs to the high dimensional world. And we're going to, in this process, we're going to define 2 types of random walks. So let's start off with what? I'm going to have 2 walks. One will be the up-down walk and the other is called the down-up walk, and you'll see what these names, very natural names. So how am I going to define? So let's take before I'm going to say, well, so I'm going to each of these walks will be walks within a layer. It will be move from one subset in a layer to another subset in the same layer. So for example, it will be a walk from an edge to an edge, or from a vertex to a vertex, or from a triangle to a triangle. Both the up-down walk and the down-up walk will be such walks, but they will use the other layers to actually do this, perform the walk. They will use the other layers. So for instance, what's going to happen? So let's look at, let's define the sort of, let's look at an up-down walk. So suppose, how am I going to take an up-down walk? So up-down walk, as the name suggests, is you are at a particular this one, you will take a step up and a step down. So if you are at say an edge, you will choose a triangle that contains the edge. You move to the triangle and then you pick any edge of that triangle, come down. So you take a step up and take a step down. The down-up walk will be similar. If you are in a particular, if you're an edge, you choose a random vertex of that edge, go down, and then you go up. By the way, this is not fully well defined because you choose a random vertex of the edge is clear. There is, if you are at a particular layer in which the hyperedge has k, this one's, you choose a random, it's 1k. Now when you go down, so suppose you are at a edge, you go to a vertex, and then you want to come up again. Which of the edges you go to, you need to define a probability distribution on this one. Let's assume that this probability distribution is sort of, I'm going to hide that fact for the purpose of this talk. You'll just choose a random one and go up. but you could define it based on the probability distribution. In particular, this, okay. So for example, this graph, you're moving from this triangle to this triangle. This is in an up-down sense. From a triangle, you're moving to a quadrilateral that contains this, and then you're dropping back down to another triangle in which another triangle which contains this. Or if yeah, it depends what people have. If you're from the simplicial community, I think they've used the word tetrahedron for things over here. It's just a set of size 4 at this point for me. I don't care what you call it. It's a quadrilateral. So there have been papers which call it quadrilateral. I think it should have been, if you're using the simplicial, it should be. It should be a tetrahedron. Yeah. So it's a quadruple. It's a 4 set. It's a 4 set. So you move from this 3 set to a 4 set which contains it, not to an arbitrary 4 set, and then from the 4 set come to any other 3 set that is contained this one. So that's the random walk. You have an up-down walk and a down-up walk. The walk's clear. You can ignore the math over there. The math is just making what I said here formal. Let's look at what happens in the case of this walk. This walk, I want to say, even for a regular, by the way, so this walk, up-down walks are defined only for every layer except the top layer because you can't go up, and down-up walks are defined for every layer except for the bottom layer. So the empty set you can't define. So all these levels except for the top and the middle have both an up-down walk and a down-up walk. Let's just look at this for a regular graph. A graph has just the empty set, the set of vertices, and the set of edges. So let's look at just the set of vertices and ask what is the up-down walk and what's the down-up walk for the set of vertices. What's the down-up walk? That's actually the simplest. If you are on a vertex, you go one set below, which is just the empty set, and then you come up, which is an arbitrary random. So this is exactly the complete graph. From a vertex, you're moving to a completely uniform other vertex. You're ignoring the edge structure of the graph, and you're going to this one. This is the down-up walk on the vertex level. What's the up-down walk on the vertex level? You're going from a vertex, you're going to an edge that participates, in which the vertex is incident on, and then you're choosing a random endpoint of it. With probability half, possibly you come back to yourself. With probability half, you go to a random neighbor of where you are. So let's ignore the lazy component in which you come back to yourself. That happens with probability half. You just ignore the other one. This is exactly the random walk that I had defined on an expander graph. That is, you take a step to your random neighbor, and the usual definition of expansion just says that on the vertex layer, the up-down walk and the down-up walk have to be close to each other. I'm ignoring the lazy component. We'll just shave off the lazy component. There are lazy components for both of them. We're removing the lazy component. The definition of expander for a graph was just the fact that the up-down walk and the down-up walk, the non-lazy part of the up-down walk and the down-up walk on the vertex layer are very close to each other. This was the definition. What I'm going to do is I'm just going to extend this definition, say a high dimensional expander, which that's true only, that this is true for graphs which have 3 layers and you're talking only about the middle layer. The other layers, I'll say that this should be true at every intermediate layer. The up-down walk and the down-up walk, ignoring the lazy components, should actually be close to each other. That's going to be my definition of expansion.
Uniformly close across all layers, and if the lambda is the same for all the layers, or
you could have a finer notion. I could have a lambda 0, I could call it a lambda 0, lambda 1, lambda k expander if this is satisfied. Right now, let's just put one universal constant. All I care is lambda is away from 1 at this point. It's a fixed constant away from 1. So we're going to expand. That's going to be our definition, the random walk definition. If for each layer, which is not the bottommost layer or the topmost layer, the up-down walk and the down-up walk, ignoring the lazy components, should be actually very close to each other. That is, whether you're walking this way or walking that way, the 2 random walks should be essentially the same. That's what I mean by this. And notice that, firstly, this does take the entire structure of the graph. It's not something which just looks at the skeleton. And for the complete K-uniform hypergraph, these 2 are actually identical. The up-down walk and the down-up walk, if you shave off the lazy component, it's actually identical. The up-down walk will just move to another. If you're at a level T, you will move from a T set to another T set, such that the intersection between the 2 sets is a T minus 1 set. So whether you're doing the up-down walk or the down-up walk, these 2 will exactly be the same distribution, the non-lazy parts. So the lambda will be 0 there. And what we are saying here, for high dimensional expanders, this lambda is something not possibly 0, but something bounded away from 1. Is the definition okay? This is right now, it's just the definition. Yeah.
So on the vertex, it goes down to the empty thing.
Yeah.
It goes up maybe to the same vertex.
It goes to the empty set is a subset of, it goes to all possible things in which the empty set is is a subset of, which is any vertex. It's going, yeah. So on the vertex layer, if you go down, then the down up walk at the vertex level is just going to a random vertex of the graph, ignoring the structure of the graph completely. We good here? So that's a definition, that's a candidate definition. That's how I'm going to define this object. Later on, we'll see why this definition is a useful definition. At the very least, right now, it takes the entire structure of the hypergraph into picture. And it extends the definition. It is a generalization to higher dimensions. Okay, this is what we'll call the random walk definition. And yeah, this is what I said. A complete K-uniform hypergraph is a 0 HDX in this sense. Lambda is 0. There happens to be yet another definition which looks more in the language of the skeleton of a graph. The skeleton is exactly this structure. If you just ignore all things above, just look at the x0, x1, x2 of a hypergraph, that's called the skeleton of a graph. One, it's the underlying graphical structure of the hypergraph. There's been another definition for high dimensional expanders that's proposed. It's called the link definition. So what is a link definition? Notice one way to define it. So with the way I had defined it, certainly the skeleton is also an expander. So this definition will also take the skeleton as an expander, but it'll ask more for it. It'll ask not just the skeleton, but several related skeletons to this graph will also be expanders. And what are the related skeletons? So we're going to define a notion called a link of a, so take any intermediate vertex, say a vertex, any intermediate subset. So there could be a vertex here, or it could be an edge, take anything. The link of that particular thing is all hyperedges that contain it. So if I was a particular vertex, the link of it will be all edges that in which this edge is a vertex is incident on, and then furthermore all triangles in which this vertex is incident on. So link of it is just the up part of every, take any intermediate object, look at its up shadow, up shade or whatever, and that's going to be what I call the link of a one. So this is how we define a link for any intermediate face in the simplicial complex. Notice that the link of every, once I have a hypergraph, I represent it as a simplicial complex, that is, it's down closed. The link of every vertex, if you, by the link, also it will be convenient for us to drop off that set completely. It's not just T's that contain S, but T minus S, because that's going to be contained in all of them. Notice that that will also be a simplicial complex. It will be down closed. So that also is a graphical structure. It also has a hypergraph structure. Depending on where this S was lying, it will be, so if the S was an empty set, you get back the entire structure. If the S was the top guy, you have nothing in it. It's just is the empty set. Depending on where the structure, this will be a corresponding layered graph. It will have K minus, if it was in the ith layer, it will have K minus I plus 1 layer. Yeah, something like that. So the definition, the link definition is of a graph is every link of every vertex. If you look at its skeleton, its underlying graph, it should be an expander. So it's this global definition that is, take the link, it's not just the link of the empty set. Take the link of any intermediate hyperedge and look at its underlying graph. That should be an expander in the usual notion. That's the link definition of a high dimensional expansion. Okay. And these were two different things. So the second thing happened was actually these two definitions happen to be equivalent. Something which is a HDX in the random walk definition happens to be a HDX in the link definition as well as other. There's a deterioration of lambda that goes when you go translate, but if this is bounded away from 1, that is bounded away from 1 also. So have this thing that these are two different definitions. One was defined in terms of random walks, the other in terms of this link, based more trying to imitate this skeleton. So take the definition of a skeleton of a graph, not just a skeleton of the original hypergraph, but every skeleton of every link should be a graph. If you define it that way, you get another notion of high dimensional expansion, and these both happen to be actually equivalent definitions. Okay. The proof is not hard. It's just a couple of pages of linear algebra, but it's not hard to see this. We'll skip the proof, but take it for granted that these two definitions are equal. Questions or? Yeah. Okay, so that's fine. We'll come to right now. So right now I've given you a definition, which is, I claim is a nice definition. I don't know if it's useful. We'll see that later on. The nice definition, it at least generalizes the notion of expansion to this one. It has one nice property. There are two different ways. Told you there are two different ways of generalization. At least one nice thing about it is the two different extensions, generalizations happen to be equivalent definitions.
Lambda prime referred in your previous definition to lambda expand that was the lambda parameter
of every skeleton of this one. Yeah. So the link definition, it's you call something a lambda link HDX if every so you take an arbitrary intermediate hyper edge and look at its link. You look at its skeleton, that should be a lambda expander, the usual notion of a graph.
I think my confusion. Lambda is some lower bound on all the.
Yeah, lambda is is an upper bound on all of these. Lambda is a number smaller than 1, which upper bounds all of these. Yeah. Yeah, so that's there. Okay, so now we could ask, before we go to application or something, let's ask the same question we asked for expander graphs. Expander graphs, the gold standard was a complete graph. Despite the complete graph having this definition, we also showed that there were very sparse versions of it, which were also expanders. That could be a degree 3 graph, which was an expander. We could ask the same thing over here. Are there sparse HDXs? Are there graphs? Are there hypergraph? For example, a 3 uniform hypergraph in which every vertex, say, participate in at most 10 triangles, even though the number of vertices is like a million or something, and yet it is a HDX in the definition we said. This is not true for the complete 3 uniform hypergraph. Every vertex participates in like quadratically many edges. So I'm going to ask the same question. Are there sparse HDXs in which each vertex, when I mean sparse over here, participates in some constant, say 10, 12, a fixed constant, an absolute constant. So in all my applications, n, think of the number of vertices as growing to infinity, and sparse will just mean the degree of every vertex is a fixed constant. How are we doing? I've not been looking at. Huh? Yeah, so So one thing you could do is you could ask the same question is, can I construct a probabilistic, can I pick these graphs randomly and expect them to be a HDX? This happened to be true in the case of the graph world. And what you can show is if you pick a random subset of what are the possible number of hyperedges you can have of K, it's n choose K. You want to pick enough, if you pick, how many of them should you pick such that it's a lambda, it's a HDX the way I defined it. What you can show is if you pick a large number of them, the number of them here is roughly like, think of K as a constant. So it's like n to the power K. In fact, let's think of K as 3 for now. So there are out of something like order n cube possible edges, how many do you have to pick at random? If you pick n square of them at random, then it happens to be a lambda HDX. The number of things is the exponent is 1 order lower. And the proof of this is identical to the proof in the graphical, in the graph case. But this is not something I'll call sparse. The number of hyperedges is quadratic in the case when K is 3. You can expect even smaller this ones. Can we ask something in which it's order n, where the exponent is order n, firstly some n to the constant, but the constant is not a function of K. Even better is actually the exponent is 1. We ask this. In the case of graphs, this happened to be nice because 2 minus 1 happened to be 1. And surprisingly enough, I don't know of a notion of distribution of hypergraphs in which I can prove such a statement. That is, I don't know of any natural distribution to put on high dimension on K uniform hypergraphs, such that if I pick a random K hypergraph, K uniform hypergraph from this, it will be an expander in the way I have defined it. I don't know of any such thing. So in fact, at this point, one might ask, do sparse HDXs exist at all? Forget about explicitly constructing them. So I don't know how to pick one. Some random one is not usually in these graphical So when you're studying these graphs, a random one has a very nice property, and we are trying to come as close to that or not. Here, random do not have the property. So first question is, do such objects exist at all, sparse HDX? And surprisingly, actually, you can construct such this ones. There are constructions based on number theory in algebra. The first constructions was given by Lubotsky, Samuels, and Vishne in 2010. This used a fair amount of representation theory. Then an elementary construction was given by Kaufman and Oppenheim in 2018. It was elementary, and the construction was elementary, but the proof was to show it was expansion was still non-trivial. It used a fair amount of representation theory. And then in joint work with Ramprasad Saptarishi, we gave an elementary proof of their construction, that why it's a HDX. It's a sparse construction. In fact, it can be as small as, you can show that it's just order n number of hyperedges, and yet it has this high dimensional expansion property that we had. If I have time at the end, and if people are interested, I can actually write down explicitly what this construction is. It's a family. So whenever we mean this, so this is almost, I take it by default, I'll give you a family of expander graphs, n going to infinity, and for every n or infinitely often n, I will be giving you a graph which has, say, at most order n hyperedges, which satisfies this property.
So I meant family, not in n, but for a fixed n.
It will be a one graph. Each of these constructions for a fixed n is one graph.
All k?
Huh?
All k?
We can do it for all k. For every k, there is a construction that does this. Yeah.
It's just n for all k.
It's n, but the constant before the n is hidden, hides a function of k. So k is going to move from the exponent to a constant out here. Yeah. No. Lambda is a fixed constant. Lambda will be like, say, 0.9 or 0.1. And I want a family for which every graph, irrespective of n is a million, n is 10 million, it has to have this feature. So the expansion is not deteriorating as n goes larger. That was the case in graphs also, and it's going to be the same thing over here. Question? So time permits, later on I'll come to this. For now, let's just take this. So nice definition and stuff. What we'll now see is ask, is this a useful definition? Are there any applications for it? So I came to this from, the reason I started studying this was more from, I'm a coding theorist, interested in building error correcting codes and stuff. And so there were various reasons from coding theory that we wanted such sort of objects, and I came to it from that point of view. So these sort of the construction of efficientless decodable codes, locally testable codes, constant query. These were some works which I was involved in. One of the breakthrough results from last year was actually the best thing to do is there's something called LDPC codes, low density parity check codes, which are very useful in the coding theory world. People used to ask, is there a quantum analog of such codes? We did not know how to construct them, and in last year, there is a fantastic work of Panteleev and Kalachev. They showed that actually you can use these high dimensional expanders to construct quantum LDPC codes. So in the coding theory, there were several works groups. At least I have been motivated to work in this area both because of its coding theory application. So also had the parallel application is to a field called property testing. But a surprising application came from a different field of theoretical computer science, which is approximate sampling or counting. That is, you have a large object and you want to count the number of objects in this. You don't have time to go over all of them. Can you do it? Or you want to sample a random object. And the theory which we built had a surprising application to this particular thing. So what I will do is actually in the next sort of 10 minutes, I'll illustrate this example, how successful this theory was in this particular area. This is work due to Anari, Garana, and Vincent. So we'll focus on this. People are interested, I can talk about the other applications later on, but my focus will be on this because this actually, I think it's a very nice application of high dimensional expanders. So I'm going to sample basis of a matroid. You don't have to worry what a matroid is. So let's start with the simplest case of this. That is, you're given a graph. Now just a regular graph. This one, you're given a graph, but think of it as a graph and have a large number of vertices, 1,000 vertices, 10,000 vertices, whatever. And there's a notion called a spanning tree of this graph. What's a spanning tree? A spanning tree is just a tree a subset of edges such that if it's connected, but there are no cycles in this. So it should be a spanning tree of the original graph given to you. Now, there are several spanning trees for a given graph. What I want to do, in fact, there are exponentially many spanning trees. If it's a complete graph, you can show that there are Petrov-log number of spanning trees. What I want is to pick a random spanning tree of these, a uniformly random. So of the set of all possible spanning trees, you want to pick one uniformly at random. Notice you cannot just go over them. You can't toss coins. You can't do this one because the number of things are exponentially large. So you want to give a process by which you can sample a random spanning tree in a given graph. And that's going to be the application. We'll show how high dimensional expanders are. Is the problem statement clear? So you're given a graph, you're given the graph explicitly, you're given vertex, you're given a graph, you're given you're given the n vertices, you're given the edge connections between them, and you have to pick a random spanning tree of this graph. So one way to do such thing is, there's a natural way is you define sort of a random walk on the set of spanning trees. That is, move from one spanning tree to another spanning tree somehow locally. Locally, let's suppose you're at a spanning tree, you'll do some local modifications, you move to another spanning tree, and then hope that this random walk actually mixes very fast in the space of spanning trees. So you run this walk long enough, hopefully that eventually you will converge to the uniform distribution, which is this one. So one way of solving this problem is to build a random walk on the space of spanning trees. Notice the space of spanning trees is exponentially large, so I can't write it down. It's too large to write it down. But we can build a random walk. So how to go from one spanning tree to some locally near spanning tree, and then ask if this walk converges fast enough. And there's a very natural walk that one can define. Suppose you're at a spanning tree. You just pick a random edge of the spanning tree. There are n-1 edges. Drop that edge. So now the graph has broken off into two components. So there are two. So you had a graph, a connected graph. You dropped off an edge. So it's a graph. The vertices are two components. There are several edges that join these two components. Just pick any one of them at random. That gives you another spanning tree. So if there could be just one the edge that you dropped, in which case you come back to the same spanning tree. That's the walk I'm going to define. So the walk is from a given spanning tree, just drop a random edge and move to the spanning tree T prime, T minus E, union E prime for a random edge E prime that connects these two components that you have broken. So this is a natural walk. This walk was suggested long ago. It was about 30 years ago. And the question was, does this walk mix well? And we did not know how to analyze this. And I want to say the theory which I just built actually will give you a proof that this walk mixes amazingly fast. So is the random walk clear? It's a very, very natural walk. It moves from one spanning tree to another spanning tree, and the difference between them is at most two edges. You're dropping an edge, you're adding an edge. And I want to say by this, if you take, so I want to say that if this walk mixes in time, which is polynomial in the number of vertices, not exponential in the number of vertices, it will move from a spanning tree, any spanning tree, to a uniformly random spanning tree in the entire graphs. Is the problem statement clear? Yeah.
It's already known that it's free from spanning.
Which? The random walk is a stationary distribution.
So that it, what do you mean? Does this walk mix?
So first thing, two things. Firstly, you're right. I should have first asked what is this? I given a random walk. Firstly, we should ask what's the stationary distribution of this random walk. This random walk, you can stare at it and say that stationary distribution actually happens to be the uniform distribution on spanning trees. And now I'm going to ask how fast does it mix, in the sense that, so it's a random, so because it's a uniform distribution, there's a random walk, it's going to eventually approach the stationary. Question is, how long does it take? So it's a walk on exponentially many vertices. The number of spanning trees is exponential. Does the walk, do you need to walk an exponential number of steps, or do you need to walk a polynomial number of steps? Mix here means polynomial number of steps. More formally, what we'll show is, if you look at the adjacency matrix of this, if you write it spectrally, if you write this transition probability matrix, that one should have, if it has if its a second eigenvalue is bounded away from 1 by a fixed constant, it's like 0.9 or 0.10, not, sorry, if it's bounded away from 1 by a inverse polynomial, is what we'll show. So it's not, If it's 1, then the graph is disconnected. It will not be 1. It will actually be smaller than 1. Question is, how much smaller than 1 is it? It's just like 1 minus inverse exponential or 1 minus inverse polynomial. What we'll show is actually it's 1 minus inverse polynomial. Okay. The random walk clear. So let's see a car. And basically what Anari et al. Showed is this answer to it was yes, that this graph, this walk mixes well. And how do we go about doing this? So let's look at this cartoon. Suppose the graph was K4. The graph has 4 vertices and 6 edges. What are the set of spanning trees of this? These are all the spanning trees of, I assume, I hope I have drawn all the spanning trees. These are all the spanning trees of this graph. Basically, we want a walk. We are given a walk that moves from one spanning tree to a random neighborhood, but I want a walk that eventually converges to the uniform distribution and converges fast. What's the walk? The walk is very natural. So from a spanning tree, you're dropping an edge. So you're moving to one of these objects and then you're going up. So that's the walk. The walk is from this layer to this. I want to say this already looks like a sort of, I've had 2 layers of the graph. So let's now just complete the picture. Let's complete the simplicial complex. So I added the other layers. So what am I doing over here? So basically, these are the set of all forests of the given graph. A forest is just set of all connected acyclic subgraphs of the given graph. So everything over here, this is an acyclic subgraph. This is an acyclic subgraph. This is an acyclic subgraph. For every acyclic subgraph, you have a vertex, and depending on how many edges are there in it, it goes to the appropriate layer. If there are no edges, it's at the bottom layer. So this, if it has 1 edge, it's in this layer, 2 edges over here, 3 edges over here. And what we are interested is, there's a natural walk going here. And notice this walk is exactly the down-up walk, which we had talked about. The walk here is a down-up walk. We want interested how well does this down-up walk converge, mix. And you have the structure. By the way, this is a cartoon. This has just 4 layers because it was 4 vertices. But if the graph has n vertices, this would actually, there would be n layers in the graph. So our question is now asking, how well does this down-up walk over here converge, mix?
You translated the original problem into a problem of high dimension.
Into a problem of high-dimensional expanders.
Whether this is a high-dimensional expander or not.
Eventually. So first let's ask why. So we're going to ask 2 questions. Is it a high-dimensional expander? We'll show you, I'll show you that it's high-dimensional expander. And let's now assume that, okay, so this was actually the main observation of Anari et al. Is this simplicial complex a high-dimensional expander? And the key result of Anari-Liogarant is S, in fact, it's a high-dimensional expander. Now the next question is, if it's a high-dimensional expander, why does it mix well? High-dimensional expander definition only says the up-down walk and the down-up walk are close to each other. It doesn't tell you that the up-down walk and the down-up walk are close to the walk that mixes perfectly well. It just says these 2 have to be close to each other. In the case of a K-uniform complete graph, this walk happened to be the one. So there's no reason the high-dimensional expansion tells you that this mixes extremely well. It says the up-down walk and the down-up walk are close to each other. These might not be the distribution that we care for. Question is, does this walk? That's what we want to ask. We are asking is the up-down walk on the top layer. By the way, in the definition of high-dimensional expander, we never considered the down-up walk on this layer, because the walk, for the definition, we always went to a layer which is one, not the top or not the bottom. And here we considered an up-down walk and the down-up walk here. We never considered the down-up walk over here, because you have to compare it against the corresponding up-down walk. There is no up-down walk. So this was not one of the walks we ever talked about in the definition of HDX. This was not one of the walks at all. But I want to ask if this walk converges to the uniform distribution, and how fast does it converge? Yeah.
Just thinking back to the original way that you constructed the layers. This doesn't look like you're going from k equals 3 to 2 to 1.
It is, no? So think of what the structures here as the vertices is not the vertices. So you should ask. So in the hypergraph edges, the underlying universe is a set of edges, and what we are putting here is you put an edge as a hyperedge if that edge is an acyclic subgraph of the given graph. So this is a subset of edges. It's these 2 edges. Yeah. So it's the HDX on the set of edges. Edges is the universe over here. In the graphical world, the set of vertices is the set of vertices of graph. But in the HDX language, the set of vertices is the set of edges. You should have mentioned this. Thanks. Okay. So let's answer that question first. Suppose we manage to prove it's a HDX. Why does it tell you that the up-down walk, the down-up walk here mixes fast? Yeah, sorry. So let's look at it. I'm going to sort of give a cartoonish proof of this. We are interested in the down-up walk on this layer. Notice the down-up walk in this layer is just a, if you write it in the language of matrices, it's an operator going from here to here and another operator going back. This one, you can write it as if you write it as a random matrix, transition walk matrix, it's a product of two transitions, one going from here to here, other one. So it's a walk, say it's the down walk, first the down walk followed by the up walk. And you're interested in this, what you care about is this, what's the spectrum of this? Is this has lambda separated away from one or not? So let's call it, so the walk is actually U, it's product of two matrices, U times D. Now, it's a nice thing about matrices that is if AB and BA have the same set of eigenvalues. Even if AB and BA are of different orders, they are both square matrices, they have the same set of eigenvalues. And the only thing that will differ is the multiplicity of the zero eigenvalue will differ. But I don't care about that. So all that will tell you is the down-up walk here is a good expander if the up-down walk here is a good expander. In fact, that's exactly true. The down-up walk, its second eigenvalue is separated from 1 if and only if the up-down walk over here, its second eigenvalue is separated from 1. This is in fact, the value is exactly the same. So now our problem, we have reduced the problem from here to understanding the up-down walk on this layer. But HDX tells you the up-down walk on this layer is close to the down-up walk over here. So now there is a loss going from here to here, but now we are asking is the up-down walk over here, is the down-up walk in this layer a good, this one. But once again, we'll do the same trick to understand the down-up walk over here. That's as good as understanding the up-down walk over here. This is just because of matrix commuting property. But once over here, this is good only if this is good. But this is excellent. Moving from, notice going from this walk is perfectly going from the vertex layer to the empty set to go back. That's as good an expander as you can, as good a walk you can get. So you do have that this is a good walk, which will imply that that will be a good walk. So it is in fact true in the definition of HDX that even the top layer's down-up walk actually mixes very fast, but that comes because of this proof. You have to chain these set of inequalities together and then you'll get the final result. So if it were a HDX, then you'll get this. There's a deterioration going at every level because the down-up walk over here it's from there to go to the up-down walk here, there's no deterioration. But from here to go here, there is a deterioration, and there will be in the next example, the deterioration happens only twice. In general, it will happen like n-2 times. And you are sure that deterioration still will not cause an effect, and you can actually check it. Now, the question now comes is why is this, at least for the spanning tree graph, why is this a HDX? Okay. Question so far. So I want to claim that if it's a HDX, you get that this is mixes first. So far, no, but this place is where it's going to use. So far, what I have shown is any HDX that the walk mixes. So far, that's all we have used so far. So far, I have only said any HDX. Now, to show that this object is a HDX, I will use the spanning tree property. So the deterioration will have a factor, depending on how many layers are there, you will have a factor them, and you can, it will, so here there will be you can write this down and it will be a multiplicative. Each time it will multiply, so as long as you're bounded away from 1 and there are only polynomially many, you'll be multiplying 1 minus mu into 1 minus mu into 1 minus mu, only n number of this ones, therefore it will be, you can, yeah. Okay, so now coming to your point, why is this where I have not so far used anything about spanning trees? All of this I said is true for HDXs. Why is that? So let's I'll do it. So what we wanted to show is, this thing going from this HDX. When I want to show the up-down walk and the down-up walk at any two layers are close to each other. Here is where I will use the equivalence, this one. So that's where so they said that the equivalence theorem says that this definition, we've used this definition of expansion, the up-down walk and the down-up walks are close to each other. This definition is identical to the fact that the skeleton of every link is a good expander. So we will use that fact, use this equivalence between them to conclude it's a up-down walk, it's an expansion in the random walk. So now let's look at a link of a, so what we need to show, I want to show the spanning tree simplicial complex. Is a HDX. In fact, what we'll show is it's a link HDX. And once again, this is the set of all spanning trees. This is forests of size n-1. This is forests of size, this is n-2 edges, this is n-3 edges, and so on. That's how it looks like. We need to show that take any forest of any particular size and look at its underlying graph. That should be an expander. So let's start with some of the simplest case. Let's take a forest over here and look at its upper, this one, and ask, is this object an expander or not? Add one more slide. So we have taken a forest. So we've taken a forest with n-3, this one. So we've taken a particular n-3. So in particular, it breaks the graph into 3 components, let's say A, B, C. Because if it was a spanning tree at the top, it's a connected graph. So now this is a connected component, this is a connected component, this is a connected component. So I basically picked in this top 3 layers, I picked a vertex here, and this vertex here I zoomed in, and this is how it looks like. Now I want to find out what are the things that look above it. So objects here, what will be here? It's going to add one more edge to it, which is basically going to be an edge. It's going to be an edge between A and B, or an edge between B and C, or an edge between A and C. So every such edge will correspond to a guy in the layer above. And what will be the layer above, finally above? So if it had connected A and B, it should be connecting either B and C or A and C. It's going to be the a tree in which this contains it. So if you look at this object, let's look at what are the if you look at the link of it, let's look at what's the graph under it. What are the vertices of the graph? The vertices of the graph are for every, so these I'm writing edges between A and B, edges between B and C, edges between A and C. For every such edge, there is one guy in the middle layer corresponding to it. So these are all the vertices the vertices come in 3 parts. The vertices come in 3 parts. Now I want to claim what is the edge structure. I could connect take any 2 of these. Is that right? Yeah, any 2 of these, and they will be object here. So if you actually look at this graph, it will be the complete tripartite graph on this one. The graph will exactly be the complete tripartite graph on this structure. But a complete tripartite graph is an excellent expander. Its expansion is, I do not know how many vertices are in EBC, EAC, EAP, but it divides a set of vertices into 3 parts, and then it's have all the edges between them. This is a fantastic expander. That's all we needed. And this proof works at every single level of it. Therefore, this is a link HDX, and the equivalence which I told you will take you from the link HDX to the random walk HDX, and that gives you the application for this one. So So this was we had come up with this equivalence between the two definitions for a completely different purpose. It's amazing that the sampling community actually managed to use this definition, use one definition to prove that this was this one, and use the equivalence to move to the other case, which showed you that the thing converges fast. So I'll stop with this one. What I had, few just. No, this is not here. Yeah, I'll stop with this. So summarizing, what we had is we defined this new object called high-dimensional expanders, which generalizes the notion of expansion to large hypergraphs. Gave some applications. In fact, we went through more or less a full proof for, except for the equivalence for sampling basis of a matroid. I gave it to the spanning trees, but exactly the same proof verbatim works for matroids too. And then been several other applications in coding theory, hoping that there will be some more applications of this object. I will stop with this.
So how do these arise in some of the mathematical things?
So math I fully don't know these two. There are topological reasons for it. At least I can tell you from the coding theory perspective where we came up with this, or at least in the quantum LDPC codes or these codes. So you're going to model the neighboring interactions with, and you want it to be a sort of efficiently decode or do some operations on them. In coding theory, you want a code, you want to, if there's noise in it, you want to use, somebody has added, you're sending a code, encoding of something, somebody has added noise, you want to recover from the noise, and all of these. So you want to have other structures that will help you in the decoding process. So if you just draw neighboring structures, you just get a graphical structure. So while studying these, it was noticed that if you had more structure on it, that is, which are the other local nodes, then not all possible ones, which are the other neighboring structures. If you have noise between these two, if I want to look at this particular, is there a related guy which I want to correct? Not. And these so naturally, these sort of, if these sort of the triangles came into the picture, that is, if I want to look at these two, if I had knowledge about this other object, then I could possibly do it. What are all the other objects that I could do it? Those are all the set of triangles which this particular edge participates in. And we wanted very sparse such object. We didn't want a set of all triangles. And then we asked, okay, if such a triangles exist, when will it be actually help for us in a decoding? We wanted some properties, and those properties happen to be these mixing properties and stuff. That's how we came about with these definitions. That is, we're looking at the space of code words and you're drawing things between local interactions. We have pairwise interactions. Now you want to understand pairwise interactions to say, talk something about them. You wanted to say, I can look at this pairwise interaction, talk something about it, but looking at some other nodes. Question is how many other nodes I want to look at. They said that if there's a small number of other nodes, which will help me to do it. But primarily these considerations came from efficiency, at least from the computer science point of view, came from efficiency. The number of others, we didn't want it to be growing in the number of vertices, but we wanted to be a fixed constant and to be able to do this. So that's why all our focus was on sparse HDXs. And we asked okay, you can have these other objects, but do such objects exist? What do we want of them? And it happened to be these random walks. That's how we came to this definition, but it happens to be useful in other contexts also. By the way, the sampling tree, the spanning tree expansion I gave you, it's not a sparse HDX at all. It's not the number of, it's not sparse at all, but it's just that the theory helped in this context. Yeah. I can give the example of the explicit sparse HDXs. All the HDXs we have seen now, the number of hyperedges a vertex participates in grows with the size of the graph. I've told you that there exist the HDXs in which each vertex participates only in, say, 3 edges, 4 edges, and they exist such objects too. I have an extra 5 minutes. I can explicitly write one. I can't prove it within 5 minutes, but I can write one and show you. It will be a construction coming from algebra, and give you an algebraic object and say this is an expander. It will be in which the number of vertices is going off to infinity, but every vertex participates only in 10 hyper edges or some such thing, but yet it will have this mixing property. We'll stop and then, yeah.